All right. Advanced Math 8. Here we got lesson 4.2.3, causation. Now we have to remember that when we're looking at our data, we can't fall in love with our data. Just because we have an association, it doesn't mean that our variables that we're using are causing each other to happen. And that's how statistics gets used incorrectly quite a bit. You see it a lot in the media, in products where they say that it has certain health benefits. It happens all the time. So we want to kind of look a little bit deeper into our numbers and see if our associations are actually causing each of the variables to affect each other. Because I'll give you an example here. It has actually been proven that as more ice cream is consumed across the country, that the number of drowning deaths also increases. What? Yes, that is true. Really happens. Does that mean that ice cream causes drowning? And if so, you should stop eating ice cream because you don't want to drown. So does ice cream cause drowning? Now we're saying that if we were to draw a graph and have ice cream down here and drowning down here, that as you start eating more ice cream, more people start drowning. That's what the data says. But does it mean that one is causing the other one? Association, just because we see an association, does not mean one thing is causing the other. Think about that. So what do you think is happening here in this situation? We'll come back to it and see if we can come up with a conclusion later. All right, so 4-80. Fire hoses come in different diameters, so you know how thick they are. And how far the hose can throw water depends on the diameter of the hose. And we've got the Smallville Fire Department, and they collected a bunch of data about their fire hoses because it's kind of a good idea to know how your hoses are working. And we got a residual plot for the data shown on the graph. So this isn't the actual data. This is the residuals. So it means they had actual data, they made a least squares regression line, and then these are the residuals from it. So what does the residual plot tell us about the least squares regression line model? Well, I kind of see a pattern here. It looks like between these numbers here, I get positive residuals, and before that I get negative residuals, and after it I get negative residuals. I'm seeing a bit of a pattern there, right? Which we don't want to see. So what does that tell us about our least squares regression line model? Since we do see a pattern in the residual plot, it probably tells us we shouldn't have used a linear model. Some other equation form might have been better. So the form of the model is probably not a good form. So since there is a pattern, to the residual plot, a linear model is not a good fit. So the form of our equation should have been something else. Maybe it should have been exponential, or maybe it should have been quadratic, or something like that. The actual form of these isn't going to tell us exactly what model we should have used. It'll just tell us that the linear form was not a great model to use. All right, part B, determine the worst prediction made with the least squares regression line. Explain what it means in context. Okay, the worst prediction will be the farthest number, absolute value-wise, from 0. And if I'm looking at it, that's 22 away. Let's see if the negatives, well, that's like 24. There's the worst prediction. So the worst prediction is when we have a hose diameter that is 3.5. So a 3.5 diameter hose has a negative, call it 24, has a negative 24 residual. All right, so what does that mean in context of the problem? What it means is the model predicted that a 3.5 diameter hose, is that inches? Feet? No, inches. So a 3.5 inch diameter hose. So here's the model. It's 24 more than what actually happened. So the model predicted the 3.5 diameter hose would throw the water 24 feet more than it actually did. Okay, so that's what this negative residual means. It means that the predicted, if you're at the predicted, your residual is 0, right? So since we're lower than the predicted, this means that the hose is throwing the water less than what we thought it should. So negative residual means we threw it less. A positive residual means that it actually threw it more than the model did. Okay, make a conjecture about the original scatter plot and what it looked like, and then sketch it. Okay, so if we had a regular, we're just making a prediction here. Let's see that we made a line and it looked like this. The first 1, 2, 3, 4, first 4 are going to be kind of close to that line. And then after that, some of them get above the line. And at 3, we had one above and below. And then we had a couple more above. Okay, so at the beginning of the graph, we had negative residuals, so the actual points were below it. Middle of the graph, we had points above the residual. Yeah, and that would be our graph there. All right, next. The mayor of Smallville finds the following graph in the town's annual financial report, not resport. That's spelled wrong. All right, so describe the association between the variables. Okay, so mayor comes over, he goes, okay, number of firefighters at a fire and the amount of property damage. It looks like as we increase firefighters, more property damage. Is it strong? No, it looks like a moderate. So it looks like there's a moderate linear, because it looks like a line, positive, because it's going up from left to right, association, no outliers, outliers, you get it, for the number of firefighters and the amount of damage. No, the pen's dying. It's like one of my favorites. It's going to kill me if this one dies. Amount of damage. Had to go to green. That hurts my heart. Part B. The mayor immediately ordered the fire department to send fewer firefighters so that the fire will cause less damage. What a fool. He's a math noob. He doesn't know what he's talking about. Why do you think he said this? Well, he said this because he saw that there was an association between the number of firefighters and the amount of damage. So he's like, well, if I want less damage, I should have less firefighters. That's why he said it. He looked at the association and saw when there's less firefighters, there is less damage. Fool. That doesn't make any sense. Do you agree with the mayor's decision? No, he's being silly. If you limit the number of firefighters, that's not going to limit the damage. It's not the firefighters who are causing the damage. It's the fire that's causing the damage. And a bigger fire will need more firefighters, and a bigger fire will do more damage. So there's other things happening than just these two variables. So we have to keep that in mind when we compare two variables. Sometimes there's other forces at work in the problem that we don't see when we just compare two variables. The firefighters are not causing the amount of damage. Maybe they are, but they'd be bad firefighters if they were. All right, 4-82. A dietitian studying the benefits of eating spinach surveyed a large sample of individuals. She recorded the amount of spinach that they ate and their physical strength. The dietitian found that the spinach eaters to be much stronger than the non-spinach eaters. The next day, the newspaper headline was, "Popeye was right. Eating spinach makes you stronger." Fools. Do you agree with the newspaper? No. Eating spinach is not going to make you stronger, right? If you just eat a bunch of spinach and then sit and watch TV, that is not going to make you stronger. That doesn't make any sense. Now, the dietitian did see that there was a relationship between the two. There was an association between the two. More spinach, more physical strength. So, what's going on here? What could explain the association other than the spinach making? Kind of like the last problem. Is there something else that we're not looking at that is actually affecting the strength other than just eating spinach? And yeah, maybe people who eat spinach have a healthier lifestyle and they work out at the gym. Maybe that's what's really happening, is that healthy people eat spinach and healthy people are stronger because they go to the gym and stuff. Okay, so maybe healthy people who eat spinach go to the gym more often. And that's why they're stronger instead of just the spinach. Okay, so just having two things associated together does not mean that they're causing each other to happen. And this is misused all the time. In health advertisements for products, on the news, in order to get a headline that everybody looks at, they use statistics improperly because they assume that just because two things are associated, that means that they're causing each other to happen. And that is not always the case. Okay, almost there. We call this a lurking variable. So a lurking variable is a hidden variable that's not part of the study. So in case of the firefighters, we didn't have the variable of the size of the fire. And that would affect the number of firefighters and the damage more than just the number of firefighters and the damage. And then in the last one, we didn't look at how much these people were working out. And that probably affects people's strength more instead of the spinach eating does. Okay, so these are called lurking variables. They're things that are associated with both of your variables that's probably causing things to happen other than just your association. Okay, a medical study found a strong link between the number of hours high school students wear a helmet and the number of concussions, so head injuries. So, some people who are fools would say, you know what? We should stop wearing helmets because when you wear a helmet, you get head injuries. That person probably has a head injury because that's foolish. So the incorrect assumption to take away from this study is that there's an association between helmet wearing and concussions. So helmet wearing causes concussions. So that's the incorrect assumption to make from this data. Even though there is an association, this is an incorrect interpretation because one variable is not causing the other one. So what's the lurking variable? What's actually happening behind the scenes that is actually causing these concussions? Well, it's probably the amount of minutes that these high school students are participating in contact sports or sports that are going to hurt their head. So the lurking variable is the number of minutes spent in a contact sport. Because when you're in a contact sport, you're going to wear a helmet. And when you're in a contact sport, you're more likely to get a concussion. So this one is related to both of these, and it's more a cause of the head injuries than the wearing of the helmet is. All right, determine a plausible lurking variable for the associations. Okay, so these are all associations. I want you to come up with your own lurking variable. Chocolate is linked to depression. Okay, so eating a bunch of chocolate, I think it doesn't cause depression, but there is an association to it. So the amount of chocolate eaten and depression are probably associated. But what else is maybe lurking as a variable there that instead of chocolate causing the depression is the cause behind it? Okay, a lack of health insurance kills 45,000 a year. If you've watched the news, stuff like that comes up all the time. Okay, these people don't have health insurance and it's killing them. There you go. Facts. It's an association. We found the truth. Okay, what's really behind it? Is it not having health insurance that's killing people? Or is there another lurking variable? How about this one? Facial tissue usage is linked to colds and flu. So does that mean when you blow your nose, you're more likely to get a cold or a flu? Or is there another lurking variable in there? All right, I think you're smart enough to figure out what's going on behind this. So find the lurking variables for these last three. That's all I got. Math hard. Look for that association not being causation. Don't be tricked. Don't be fooled. Math hard. See you guys later. Bye.